This is lecture 8, and this will be the final lecture for chapter 3. In this lecture, we're going to talk about more about simplifying systems of forces. So you may recall that in lecture 7, we talked about the idea of an equivalent force couple system. And this lecture really doesn't add a lot new to that. It just shows, or I'm going to show you a few examples of how you deal with more than one force and how to reduce that. So let's go ahead and get started. So this is a good pictorial, because recall that if we have multiple forces acting on a body, in this case we have F1, F2, and F3, acting on a body that the respective points A1, A2, and A3, and we want to replace those three forces with a single force couple system at O, we know that in order to move the force to O, we have to add a moment. So the easiest way to do this is first sum the forces. So the resultant, because again, we're finding an equivalent force couple system, which has two answers. It has a force and a couple, or a moment, synonymous. So first we just add all the forces together. So you just take the IJK components of M of F1, F2, and F3, add them together, and that's your resultant. That's all you have to do. So that's half the answer. Then the other half is you want to figure out what is the R vector, or distance vector, from the point that you're moving everything to, in this case O, to the location of the force. So in this example, our blob on the screen, we have three forces at three separate locations. So that we have to find three separate R vectors, R1, R2, and R3. And then it's just a question of doing the cross product. So to deal with F1, we'll just do R1 cross F1, and F2, we'll just do R2 cross F2, and R3, we'll do R3 cross F3. And so you can, in the equal signs, the blob next to it shows you how what they have done then is they have created those moments, M1, M2, M3, with all the forces emanating from O. And then finally, you take those three moments and you add them together. So just like you'd add vectors, you add their respective IJK components, and you get your final vector. And that's it. So it's really no more complicated than what we've been doing. It's just adding a few extra components. So let's do a relatively straightforward example. In this case, we have some machine component. It has forces acting on it in different directions. Now, this type of problem here, in some cases, you can just literally do force times distance and add them together. I find using R cross F works well, because then you know that's going to work in any situation where the direction of the force isn't as clear cut as this. So here we have our system, and hopefully you took a moment to write down the draw it yourself. If not, then rewind the video and look at that. And then let's go ahead and solve it. Now, as we know, we want to solve, we want to have the sum of all forces. That gives us our R. So we want to figure out what is R. So let's do that first. So we have our forces, we have the respective forces at respective locations, but the points don't matter because we're just looking at what are the directions. Now these forces are all in specific directions. So first off, we have at point B, actually, let me write this. So R is going to be equal to the force at B plus the force at C plus the force at D. And so we don't want to get ahead of ourselves. So this is our governing equation for that. So if we do that, we know that the force at B is going to be negative 240 in the J. That's this one. And it's also going to be minus 125 in the K. And then we look at the force at C. That's just simply negative 300 in the I. And lastly, the force at D is just going to be a positive 150 in K. So we have those. So if we add them together, then our resultant force, which is at A, equals negative 300 I minus 240 J and plus 25 K. All right, so that is part of our answer right there, just that. So we have that. Now we're going to use that again because we're going to come back. Actually, we're going to use the individual forces, but so that's half our answer. So going forward now, we know that if we want the moment at A resultant, MAR, then we know that's just going to be equal to the sum of all the R cross S. So another way we could write this as the sum of R B relative to A crossed with FB plus R C relative to A crossed with FC plus R D relative to A crossed with the force at D. And so those are three. Those are going to equal our resultant. So then from here, this is just like we've done before. If you ignore these two, then really all you're doing is you're finding A relative to B, or going from A to B and crossing up the force. So in the previous lecture, we'd have been done there. The only difference now is we're just adding. So going on, let's go ahead and do that. So we have let's figure out our respective distance vectors. So RB relative to A, and what is that going to be? Well, that's going to equal to 120J, okay? And that's, again, millimeters. So millimeters and newtons I put up here are the units. And I apologize, sometimes I jump around. But it's good to keep track of your units in the interim. Sometimes it's easier just to define them at the beginning and then just leave them unitless here. Some may say that's not good, but that's good for now. So RC relative to A, and that's going to be 60I plus 30J minus 75K. And then lastly, RD relative to A, and that's going to be equal to 60I plus 80J minus 75K. And that's it. So we have that. We have the respective forces. So we go ahead and set it up. So if we set up our moment about A, resultant, then what does it look like? So RB relative to A is going to, and J, so we have these just so RB relative to A, force of B. So we have 0, 120, and 0. And then our force is going to be 0, negative 240, and negative 125. And then plus our C relative to A, and that's the force at C. And that one we're going to have 60, 30, negative 75, and negative 300, 0, 0. Sorry. And then last, we have plus, and I'm going to put that down here, RD relative to A, force at D. And then that one we also have 60, 80, negative 75, 0, 0, 1, 50. All right. So I know you know how to do this. So the result is once we do the crosses, add everything, all the components together, we get negative 3.00 plus 13.50 plus 9.00. And what I've done in this is I've converted from millimeters to meters. So I took the answer, and this would have been 3,000, 13,500, and 9,000. And this is in Newton meters. You can leave it as millimeters. I just find it's a little more clean if you do it this way. And so that's your moment at A, resultant, right here. And of course, this force here. So your final answer, you'd box this, and you'd box that, and then you'd be done. So that wasn't too bad. So going back, then we have another idea or another type of problem is where you have forces that are parallel all on a single object. And so the idea with this is that the parallel forces can all be replaced by one single force. And you can see this here with that. We have F1, F2, F3. They're all in the J direction. So we can replace them with a single in the J. But then the question is, where should that force be applied so that it creates the same state as when they're here? And so, for example, each of these forces has a X and Z location. So what we do effectively is, and as the equations show, is we first sum the forces, and then we sum moments about the x-axis, where we take the force 1 times its z location, force 2 times its z location, force 3 times its z location, and we set that all equal to r times z resultant. So in this equation, the only thing we do not know is z resultant. We do the same thing, summing the moments about the z-axis, only in this case we use the x component, and in this case the only unknown is the x component, or I'm sorry, xr. So once we solve that, now we know where we could put a single force and at what location so that this system would behave identically. So let's do another example. So in this case, we have stage lights, and in our stage light, we have the light A and B both weigh 4.1 pound, and light C has a weight of 3.5 pounds. And we're given the value for D. So what we want to know is if let's say that D and E are perfectly balanced, and we want to replace those 3 lights with one giant light that weighs the same as those combined. If we were to do that, where on this bar DE could we put this so that it would be the same equivalent stress state or force state? So let's go ahead and solve this. And actually what I would say is, before you go on and watch the solution, is try this out yourself. Again, the more practice you get, the better and the easier it's going to be with the quizzes and the exams. Let's try it out. Okay, so you've tried it out, you've gotten the answer, that's good. So let's go over it. So here we have our diagram. So what we're trying, this is what we started with, 4.2, 4.2, 3.5 at the respective A, B, C locations. We have our given, and we know what our find is. So really what we're trying to do is we're trying to find this distance and that magnitude that would be, and so effectively these two would be equal, all right? And so, I don't know, equal should be up and down, or if it should be like this, but neither one really looks good, but this is that. So how would we do that? So the first thing we want to know is, what is the sum of the forces? And all the forces are in the y, so that's going to equal our resultant in the y. And so that's just going to be our y is going to be the sum. We do 4.2 plus 4.2 plus 3.5. We do the complex math, get out our calculator, and we get 11.9 pounds. Okay. So we have that. And so then the next step is we're going to, because we know this value now, 11.9 pound, then we want to find what is this distance. So we can think of it as a series of moments. We know that 11.9 pounds times this distance is going to be the same as the sum of this force times that distance, this force times this distance, and this force times the entire distance. So let's go ahead and do that. So sum the moments about D. And now what you will see in some of the solutions and in the book is you'll see sometimes they do this, where they put the arrow going that. That just indicates, in this case, that we're saying that clockwise is positive. And the reason we do that in this, normally we say clockwise is negative, but the reason we do this in this convention is that it's easier to write it all down if everything's positive. The convention really doesn't matter here because all the forces are causing a clockwise rotation with respect to this point here. So we redefined it as positive. We get the same answer if we did it the other way. The only difference is we'd have negative, negative, negative equals negative, and they'd cancel. So it's just more of a bookkeeping thing as opposed to any kind of fundamental change. So we go ahead, we know that 4.2 times 10 inches, and never do the double tick. Sorry about that, force of habit. So 4.2 times 10, we'll just leave it plain, plus 4.2 times 44. And so that's just 10 plus 34 gives us 44. And now we're given that D is 25. So we know now that plus 3.5 times 67. That's going to be 44 plus 25 gives us 67. And all of that equals the resultant times the x. Okay, and that's what we want. So we know the resultant. We can plug in 11.9, right? If we do that, then we solve for x. And it gives us a distance of 38.8 inches. And that's right of D, because that's how we defined it, but that's where it has to be. So we know that this distance here is 30.8 inches. And therefore, if this piece of material, whatever it is, will not know the difference whether I put all the weight here at that length or if I distribute it there. Now, again, in the real world, this isn't completely true because this material might be, as we know, the strength might be able to handle hanging the weights distributed, but if we try to put all the weight at one point, it might shear. But again, in this class, we're assuming it's a completely rigid body, and that's not an issue. Okay, so let's get another example. So this example is a pier, and it's very similar in an approach to what we just did. And you may remember this from an old movie called Creep Show, where they swim out to the pier, but then they get stuck there because this black blob, it eats whoever leaves. So it's a Stephen King book, which are generally good, but his movies in the past were fairly atrocious. Anyway, so here we have our 3 people standing on there, 3 children, and we have a 5 by 5 meter raft. And this is really what we're trying to do is we're just trying to replace the 3 children with one single person. So if one single person, let's say in order to rescue 3 children from the blob, you had to leave one single person, maybe a graduate student, because there's plenty of them that can be sacrificed easily. And so maybe we'll put that person at this location. Where would we have to put them? And that's what the calculation is. So I would go ahead and try it yourself again. You know the resultant's going to be the sum of these 3 weights, and then you're going to sum the moments about the z to get the x-axis or the x location, and you're going to sum the moments about the x to get the z location. And once you have it, you have the result. Okay, so you actually, let's go ahead and do that problem. So I'm going to go ahead. So there's our drawing. So let's go ahead and do this. So first off, again, we know that our R is our resultant. It's just going to equal the sum of the forces in the y direction. So in this case, we know that if we add everything together, we're going to have 385 plus 240 plus 415, and that gives us a total of 1040. So there's our R. So we know we have 1040 newtons. So now we're going to sum the moments about the Z. We know in that case, that's going to be the force at A times XA plus the force at B times XB plus the force at C times XC, again being the weight, the respective weight of the children times their location. And then all of that's going to equal the total resultant times the X location. Okay, so if we go ahead and put that in, we have 385 times 1 plus 240 times 1.5 plus 415 times 4.75, and that equals 1040 times XR. So divide both sides by 1040, we get XR equal to 2.61 meters. So we know XR, that's the X resultant, and I probably should have called it this so I wasn't be consistent. So this would be our XR up here. This is our XZ. Sorry about that. So go ahead, do the same thing. Sum the moments about X. And in that case, we have the same FA, only it's times ZA, FB times ZB, FC times ZC. This is their Z locations. So in this case, I'm just going to write 385 newtons times 3 plus 240 times 0.5 meters and 415 newtons times 4.75 meters. All that equals 1040 times ZR. Solve for ZR. And we have 3.12. So there we go. So we know this is 3.12, and that's 2.61. So now we have the very exact location. We can drop the graduate student off right here to extract the children at the same time. Graduate student lives out their life on the raft until the blob gets them. That's the end of the story. All right. Okay, so the last part of the chapter talks about how we can reduce, even if we have several moments and resultants. So for example, even if say we found this equivalent moment resultant that we did with say the first example, and we had it at point A. So then the first example, we took all those forces, we found a moment and a force at point A. Even once you're done with that, if you want to go ahead and move that to a new location, then you just do the same thing as you did in the example in the last lecture. And what I mean by that is you just simply take that moment, find its components, and it's because remember, a moment's free to rotate, so that moment is still there at point O. You move it to O prime, and then you do the distance S crossed R, and you add it all together. So I don't tend to give problems like this on tests because they get very tedious and long. But the idea is that it's no really different than what we're doing. It's just saying that if you combine all of your moments and forces into one moment force system, you can then move it again just simply by using R cross F and moving the moment. That's all. Okay, so I have one last example I'd like to show. And this one's a little more complicated, but it kind of encompasses everything in this chapter. Now in subsequent chapters, we'll be dealing with rotating. I mean, they're not rotating; they'll be static, but we'll be dealing with journal bearings. And in this case, you can see that the types of bearings that this belt system is on, they can support force in the Z and the Y direction, but they can't support force in the X direction. And so, and to show you that, and this is a matter of practicality, here's a radial bearing I've showed, and that's FAG is one of the major distributors and manufacturers of bearings. You can even see it written on the bearing if you magnify. But in this case, if you apply a force that's in plane, then the bearing is very, very strong and can support a lot of weight. But if you put any kind of a lateral force in the bearing, you tend to pop the balls out, and it isn't functional. It's not designed that way. Now, I include a thrust bearing also to show you the difference. So a thrust bearing can take force in that radial direction. So there's just two types of bearings for two types of uses. The reason this is important is when we get into chapter 4 and beyond, we'll be faced with finding reactions at these locations. And we want to recognize that because this type of bearing can't support that, we don't have to worry about any kind of reaction in the X direction. So anyway, so let's go ahead. Now this problem we're going to solve, and we're going to look at it as how do we take these belts and that are rotating at constant speed about the x-axis, and how do we apply the force that is in the system and move it all to A, to the journal at A. So how do we do the equivalent force couple system at A? And that's the question. So for one is if you look at the drawing, you can see that the force at C wants to pull the shaft so that it rotates about the y-axis. So if you think of the y-axis and you think of the moment arm as AC, the shaft distance, then that force is going to want to rotate about the y-axis. If you look at the force at B, it's going to want to rotate about the z-axis. Now, because both C and B have slight angles to them, it's not going to be a pure rotation about the y and the z respectively. There's going to be a small component in C's case that's wanting to rotate about the z, and a small component in B's case that wants to rotate about the y. But neither of those belts is doing anything about rotation about the x. So you might say, well, then there is no x component, but you have to consider the rotation of the force times the width of the pulley, because that's creating a moment also. So ultimately, we want to figure out all three of these moments, and we want to add, actually there's 4, and add them together and add the resultant force together so that we can have our equivalent. So if you can do this problem without any help, then you've pretty much mastered most of the material in chapter 3. I'd say you're in very good shape. So go ahead, I would say take a stab at it, work at it, see if you can't figure it out, and then come back and we'll solve it. Okay, so took your best shot. Hopefully you solved it. If not, don't feel bad. It's a little more complicated. So here's my drawing. So I have my newtons here, I know this is in millimeters, 225, 225. We really don't care about anything beyond this. This D bearing, there's no external force applied to it, so it doesn't do anything. So we can pretty much ignore it. We're only concerned with C, B, and the forces on that. So the first thing, we want to find an equivalent force coupled system at A. That's our governing equation. So how are we going to do that? Well, the first thing is I want to look at are the rotations. Now I mentioned that these pulleys have different forces. Now if I drew the pulley, and so the pulley at B is rotating about the x-axis. So, and that rotation about the x-axis is going to be 145 newtons that wants to go counterclockwise, which is our convention's positive, and the 215 wants to go the other way or clockwise, so it's negative. So we take that minus that because they're opposing, and we multiply it by the radius. So the radius is 150 millimeters, so 75 millimeters is the radius. And it doesn't matter that there's an angle here because the belt has to leave the pulley at a 90-degree angle, which means it's in contact. So even if that's up here, it doesn't matter as far as the moment goes. So for this one, we get a negative 5.25 in the I direction. If we look at the other one, the 155, 200, 240, it's the same. The only difference is the 240 going in the counterclockwise is bigger than that. So we end up with a positive. So we get 6.38 Newton meters in the I direction. So that's a start. So now we want to consider what is let's look at B and look at C. So first thing, and we're going to add all this together. So we'll say, what is the resultant of B? So we know the resultant of B, and this again is the force resultant of B. We know that we have 145 newtons, and that's going in the negative J, so it's cosine of 20 degrees. Sorry, this is 20 degrees here. 20 degrees J. And it's also going in the positive, and this side of it is the positive Z, so plus sine 20 degrees K. All right, so we have that. And then minus 215 J, and that's what we have. So if we combine that, the reaction at B gives us negative 351.3 J plus 49.6 K. So there's and that's 215, not 2 divided by 5. So there we go. That's our reaction B. That's just the force, okay? Then we do the same thing. Actually, before we do what we're going to do now is, remember, we'll find reaction at C also, but let's stay with B for the moment. So when we're with B, remember that because there's a force here, the fact that we're moving this force to A, we know that this force, again, is having a tendency to want to rotate about A. So we have to compensate that. So what we can do then is we can say the moment about B that is create. Oh wait, I apologize. Back up. Actually, I'm sorry. I'm going to go ahead and find RC, and then we'll come back to doing the cross. So RC, then, this is why I hate not being able to edit. So RC is going to be equal to, and if you think about RC, it's 155 newtons, and it's going in the negative Z direction. So, and we also have 240 going in the negative Z direction, and they're both at the same angle. So what we can do is we can combine those, but maybe it's easier just to say 155 times the negative sine 10 degrees, because that's this component that's going in the negative j, minus cosine 10 degrees in the k. And so that would be, so this part of the 155 is going to negative k, so it's 155 times cosine 10, and this part here is going down, that little part is going to be the j component. So I have that, so it's that times that, and then I have the same thing. This is going to be plus 240, and that's also going to be times minus sine 10 degrees j minus cosine 10 degrees k. And so as you can see, it might have been easier just to add these two together beforehand. So we end up with this is negative equals negative 68.6 j minus 389 k. So that's my reaction B. My reaction C. Now, so the next thing that we need to do is, for one, is we're going to add those together. So because we want our total force, so we're going to go ahead and add those. So if we add these, if we add this to this and this to this, we should end up with negative 420j and negative 339k. And there's a little rounding there, but yeah, so that's my R. So that equals this, and that's newtons. Okay, so all I did there is these are all the forces acting on this. They include this, 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 and this, and that's where they're acting in that direction. Notice there's no force actually in the x direction because they're not in that, so we only have moments. So then we have that, so what we have to do now is we need to figure out what is the moment at A. So that's going to be equal to the moment at B plus the moment at C. Now remember, those were this and this, but we also have to add to that R, B relative to A, crossed with the force at B, and then plus RC relative to A, crossed with RC. So what we're doing is we're taking the distance from A to B, crossing it with whatever that force was at R, B. So we have that up here, and then we have RC right here. Okay, write that down. So let's go ahead and set that up. So we have RB relative to A and RB. So we know that from A to B is just 0.225 or 225 millimeters, 0, 0. That's the distance from A to B. And we know our RB, going back to this, is just that value there. So we can put in 0, negative 350, 1.3, and 49.6. Then we're going to add to that RC relative to A and RC. So in that case, we have the distance is 450 millimeters, or 0.45, and then 0 in the J and the K. And then RC, we just apply, and there's that. So we have 0, negative 68.6, and negative 389. All right. And so clear 0, there's that, and so forth. And so there we have that and that. So we do our cross product and we add everything together. So pretty much we're going to do our cross product This is going to give me negative 11.25J minus 79K. This is going to be 175J minus 31K. And then, of course, we know that we have the J and the K, so we add them. And so MA plus MB gives us negative 5.25 I plus 6.38 J, or essentially 1.130 I. Okay, so I know it's going a little fast. So this here is the only moment about the I, and that's just from this rotation that we found here. So we had to add them together. We had a negative and a positive, so they counteract, but this is bigger. So our net moment about the I is that. These two here are our net moments about the J and the K. So if we add this to this, so negative 11.25, we get plus 163.8. And if we add the 79 to 31, we get essentially 110. So plus 110.0. So J and K and I. So moment at A equals this, and that's all in Newton meters. And there's your answer. So your answer consists of this and this, our force couple system. Okay? That was long. All right. So go ahead. I think that's the last slide. Okay, I thought for some reason. Oops. Okay, that was, I apologize, that was my last slide. So I thought I had a summary, but I will actually, what I generally do is I do post a summary for the chapter, and that's something I put in with the study guide for the exam. So that's pretty much it for chapter 3. Hopefully these sections have been fairly straightforward and you understand them. But coming up in the next lecture is chapter 4. We'll start talking about equilibrium. And so real quick, I want to just point out that when you're trying to evaluate the class, one of the things I noticed is that if you were to plot difficulty versus time, say weeks, then it's almost spelled like this sometimes, weeks. It starts out kind of like this. It starts out kind of like this, jumps up in chapter 3, plateaus again in 4. So that would be chapter 2, 2, 3. That's one nice 3. And then 4. And then, of course, it goes like that. No, I'm kidding. Then it just goes back again. So 4 is actually a fairly straightforward chapter at the beginning. Then it gets a little harder. And then we get into trusses and things. But none of it's not manageable. So none of it's not manageable. Nice. Okay. Well, that's it for this lecture. Thank you for listening. And I'll see you in lecture 9.